Okay, so what we call this problem is, we call this problem is multi-stage graph. And in this problem, what we do is the graph is structured in a specific format. What's that format? Let us look into that. So in this case, it's a directional graph. I mean, here you have a directional. It doesn't mean, like you can see here, it is from 0 to 1. It doesn't mean 1 to 0. You can see all the edges are directional. And in this directional graph, apart from being directional, the vertices here are partitioned into stages. For example, I'll call this as stage 1, stage 2, stage 3, and stage 4. I mean, all the nodes in this, they come under one stage. Then this is the next stage, and this is your last stage. So stage 1, stage 2, stage 3, and stage 4 vertices are partitioned that way. And all the edges, so whatever the edge you have, u, v, they are such that u belongs to stage I minus 1 and v belongs to stage I hope you can observe that here. So for each u and v, take any u, v edge, a pair of u and v, you will see that u belongs to previous stage and v belongs to next stage. So when a graph is structured in this format, we call it as multi-stage graph. So given the graph which is structured in that format, our problem here is to find a minimum distance between source node and sink node. What do you mean by source node and sink node? So when I say source node and sink node, it indicates source means this 0 and sink node means the last node. So everything emits or starts from the source node and everything gets and comes and ends at the sink node. So what we need to do is we need to find out a shortest distance between source node and the sink node. Let us call it a last node, first node and last node. Let us call them as first node and last node. So we need to write an algorithm for that problem. So by now looking at this approach, the easiest approach which first clicks to our mind is to apply a greedy approach, right? So let us assume that I start at this node and I keep on selecting edges in each stage based on the minimum cost. For example, from 0 to 7, I want to find out a minimum cost path, right? So here in this case, let us suppose if I take an approach where I start with first node, then I select the minimum. So what I said is let us use the greedy approach. Greedy approach means I keep on selecting the minimum possible from the outgoing edges and I keep on following that. If I do that, let us see will we be getting a solution or not. So first let us try a greedy approach. So what we do is we keep on selecting minimum edges from outgoing edges of each stage till we reach last node. So if I put this approach, so what would the first edge I will be selecting? The first edge I will be selecting is 0, 1. And what would be the next edge I will be selecting? If I have reached to the stage 1 from stage 0, I have reached to stage 1. So from stage 1, I need to find out 1, which is the least. So since I have reached 1 here, the only possibility to me are these two edges, 4 and 11. If I select minimum of that, then it would lead to the selection of edge 1, 4, right? And once I reach to the stage 3, I need to find out minimum from 4 outgoing from the 4. What is minimum edge which is outgoing from 4? Is the only edge we have 4, 7. So if I go by this approach, what's the cost? What's the total cost I'm getting? So 0, 1 means 1, 1 plus 4, 5, 5 plus 18. How much it is? 23. Is it minimum? Is this minimum distance between my first node and last node, which is 7? What do you say? Is it minimum, or are there any further minimum routes? So we need to agree if we can use the greedy. If we cannot find a solution by using greedy approach, then we look for some other approach. So those who have been following, you can tell me that when I go from 0 to 1 and when I select the approach based on this greedy approach, what I am getting is 23. Is it minimum? No, it is not minimum. You can see that there are far more minimum routes. For example, you can see this 5, 2, 2. It's a 9. I think this is a minimum one. This is the minimum route between 0 to 7. So if I apply this greedy approach, I won't be getting any solution. That's clear. So we won't get any solution if I use greedy approach. So what I'll be using? I will use another approach. Now, should we call that another approach as a dynamic or divide and conquer or some other approach? Let us take the decision at the end of discussing the solution. So now you can see that the problem with greedy approach is I am starting it that I am choosing minimum, but I don't know with the minimum cost which I am going here, I am not sure if it leads to the minimum to 7 or not. So I need to find out, I need to decide, I need to make a decision. The decision is choosing a next node in the next stage, so that that choice which you're making, like whether to select 1, 2 or 3 in the next stage, will that choice lead to the optimal solution of shortest path to the end node, which is 7? That's what we have to look for. So what I need to do is, from 0, I need to select such a node in the next stage such that which will lead to the minimum with a minimum cost which will lead to the 7. So once I am into this node, what I need to do? So I need to select something which is minimum of these 3 nodes. Then I need to select minimum of these 3 nodes. Then I will be selecting minimum of these edges. Are you getting that? So if I say, let us suppose, if I write cost, if I say cost of or else let us do one thing, instead of calling distance, let us call it cost calling, let us call it as distance of node 0 and stage. Okay, so let us use some convention. So what we will do is we will use this convention, distance of 0 comma 1. So when I say distance of 0 comma 1, what I am referring, since this problem is fixed, it means that I have to always find the shortest distance to the last node, which is my sink node, right? If this is fixed from source nodes to sink node, this is fixed. So what I will do is I will refer, let me write it here as well. So what I want, what convention I want to use is I want to refer distance. I'll say node comma stage. That's how I'll refer. So if I say distance 0 comma 1, what it should indicate? This should indicate distance from node in a stage. For example, if I say node n and stage s, what should that indicate? This convention of writing this node n comma stage s, it should indicate distance from node n in stage s to the last node. It should indicate that. This is what I am referring when I say distance of n comma this. For example, let me minimize this. I hope you can still see this. Let me highlight that. Okay, so that's what. So if I say distance of 0 comma 1, what it indicates? Distance of from node 0 in stage 1, node 0 in stage 1 till the last stage, which is node 7. So how should I, what it would be equal to? This would be equal to the cost of edge, let's call C. Let's say, indicate C to indicate cost of edge. What edge I want? 0, comma 1 plus, there are multiple possibilities, right? So cost of 0 plus 1 plus 1 plus distance of node 1 in stage 1, right? This is one possibility. What is another possibility? There could be one other possibility to this. What is that? Cost of node uh, 0, cost of edge between node 0 to node 2 plus distance of node 2 in stage 1, right? This is one possibility. I mean, like, if I select this edge, then the total cost to reach from 0 to 7 is the 2 plus the distance, the minimum distance which I will require from 2 to 7. From 2 to 7. That's what I'm saying, that this indicates, means distance, what it indicates? Distance from node 2 in stage S to the last node 7, right? There is one more possibility. Since 0, 1 has three edges here, I have one more possibility here. What is that? Can you guess? Cost of, well, there is one more at 0, comma 3, cost of at 0, comma 3 plus distance of node 3 in stage 1 to the end node, right? So I have these three possibilities. So what will be this entire distance here? It will be minimum of min of these three values. I hope you're getting that. So it is a minimum of these three values. That gives me the entire distance, right? I hope you're getting to this point, right? Okay. Now what's remaining is, can I solve this now? As of now, I know these values. Cost of at 0, comma 1. Let me also write C of u, comma v. What does this indicates? Cost of edge u, comma v. So if I use that convention, this indicates this. Now if I want to find out 0 to 1 distance, what I need to do? I need to find this distance 1 and 1. I need to find distance 2, 1. I need to find distance 3, 1. Now when you're finding distance 1, 1, you can see that. Now let me find this value. In order to calculate value for this, you need to compute this. So now if you want to compute values for distance 1, comma 1, what you will have here? Once again, all the possibilities you will check. Minimum of, what you'll have here? You will have a minimum of, okay, how many outgoing edges one has? So one has two outgoing edges. So edge cost, what is that edge cost? Cost of 1, comma 4 plus distance. What I need to do? Plus distance. See, by using this edge 1 to 4, I reach to the next stage. In the next stage, what node I am reaching? Node 4. So plus distance of node 4 in stage 2, so that it reaches 7, right? This is one possibility. What is another possibility here? Since I has this 1, it's 2 possible. So from 1, I have one more outgoing edge to 5 plus distance of 5 in stage 2, right? This will calculate 1, 1. So on, you have to calculate distance of 2, 1, distance of 3, 1. That will further figure out. So now if you look at this, it will once again call for one more thing. This will call another one. So on till you reach to a stage, where you will make a call to distance of, what you let distance of node 7 in stage, see, if it is stage 1, stage 2, stage 3 and stage 4, Distance of node 7 in stage 4, what it would be? 0. We have to reach 7. I am at 7. What is the distance? Distance is equal to 0. Right? So that's how we have to keep on computing this value 1 1 2 1 3 1 and then 4 2 5 2, so on. You will get that. Now if you try to look at this, this would make a recursive call. It would create a big recursion tree, right? So at the same time, now you have calculated distance 1 1, right? So let us see, if I calculate distance 2 1, if I calculate distance 2 1, let's see what it will have. So how would you calculate distance 1? Minimum of how many outgoing edges 2 has? 3 edges, right? So it will have 3 such values. Let me write. So okay, so from 2 to 4, this edge I am talking about, this 2 4, 2 5, this 2 5, and this 2 6, this address I am talking about. So from 2 4, once I reach 4, what should I do? The distance remains same. The cost of reaching to the destination node 7 in stage 2 for node from node 4, that's the meaning of this distance, right? This is one thing. And what else I'll be adding here? What else I'll be adding? This is one node, and I think likewise we'll have P search for this one. Just okay. Let me expand this little. Okay. So that is 2 4 and 2 5. Then node 5 stage 2. Then I have 2 6, right? One other edge for this is 2 to 6 plus distance of 6 in stage 2 to the end node. So when you are here, you will understand that. Okay, and all this further remains same. So let me put just a dot 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 so that it indicates that I am reaching to this end. Okay, so now if you look at this calculation, when if I keep on recursively calculating, if I draw a recursive tree, you'll understand what exactly it is. Now you can check here, I am calling distance of 4 to here. So if I say I am using a recursion, I am making a recursive call here, and I am making the same recursive for calculating 4 2 as well. I am using the same recursion call. So for 1 1 I am calling this, for 2 1 I am again calling this, for 3 1, if from 3 to 4 we had a head, we could have called it. So for example, here you can see that once again you can see that phi 2, you can see here phi 2, and the same phi 2 is being once again called, this phi 2 is once again called at this when you're calling 2 1. So you are making lot of repeated recursive calls. Now you can now guess a solution to this, a design approach. What would be the design approach? If you think of, I am starting at this, I'm making a recursive calls and recursive calls and recursive calls. So what if I start computing from this end, right? So I'm starting from here, I'm finding minimum at this stage, then I'm going minimum, then I come back and somewhere I get that. So if I go on an approach called as bottom up approach, since I see this multiple approach, I can say that this problem can be solved by using dynamic one. First, what is the first thing? It is obviously a optimization problem. It is asking me to minimize some values, and I can see that it is recursively calling to a sub problem. I can see a sub problem, distance of 1, then distance of 1 2 2 1 3 1. So I can see sub problems here, And I can also see that some sub problems are being solved multiple times, 4-2, 4-2, 5-2, 5-2. So this perfectly fits into the principle that the features of dynamic programming. So now I am sure that I can use dynamic programming. I have two approaches. One, to apply a recursive approach. The second one is in bottom-up approach, wherein instead of recursively starting, what I'll do, I'll start with this basic, the smallest block. So I'll start from distance of 7 in 4-2. Then I will start with distance of 4-5-6. Then I will start distance of 1-2-3. Then I'll start with 1. So that should make the without any recursion I should be able to solve. So as you can see that if I want to calculate anything at stage I, if I want to calculate distance at stage I need to know the distance at stage I plus 1. So if I want to calculate distance of this, I need to know this distance of 4, 5, 6. So do you see the pattern? Like before I calculate distance of nodes in any stage, I need to calculate distance of nodes in in its following stages. So what I'll do, I'll start with 7. I'll compute this, then I'll do that, I'll compute distances, then I'll compute this distance, and then I'll come here, then that will lead to the final one. So these edge costs are something which are there, all I already have, I need not compute them, they're already fixed. Are you getting? So what we do is, given this entire uh, calculations from distance to this, what we will do is, let us do one thing, we'll start computing this from backwards. Now for that, let me make a space here. So let us see in a dynamic programming approach. So if I say that I'm starting with something called as bottom-up approach, then let us do one thing. So what we will do is, first we will compute distance from backend, right? So what the first thing I can compute? Distance of last node in last stage. So it is stage 1, stage 2, stage 3, stage 4. So what I'll say? Distance of 7 in stage 4. What it is? 0. I know this is 0, right? After that, what I'll do, I'll compute distance of all nodes in stage I minus 1. If it is at stage 4, then what I need to do? I'll compute distance of all the nodes in stage I minus 1. How many nodes I have in stage I minus 1? 4. Stage 3. This is 1. And what are others which I have in that? Stage 4, node 4, stage 3, node 5, stage 3, node 6, stage 3. Okay. So to compute this, what I need? The edge cost. Edge cost I already have 4 to 7. What is 4 to 7? So how do I write? Cost of from 4 to 7. So whatever are outgoing edges from 4, whatever are outgoing edges from 4, the cost of that, so it will be min of cost of C3 plus distance so by using it's not 4, it's a 4 7. From 4 7 I have edge plus distance 7 in that stage, distance 7 in next stage, distance 7. What is that 7 here? 3 plus 1 in the next stage. So 3 plus 1 means distance of 4. So this I already computed. So minimum of min of this, or I have only one edge in that, right? So what this cost will amount to? This will be 18. I hope you're getting. What is this? This is 18. Likewise, okay, likewise, I'll get it for 5. What will be it for 5? Can you guess what will be for 5? So from 5 to 7, edge 5 to 7, and distance of 7 in 4. What is 5, 7? 13. I think you will get here it is 13. And likewise, you will also get it for this for from 6. 6 to 7 plus this. What it is? 2 plus distance of that. What it is? 2. Are you getting? We have computed all distances in stage 3. Now what I'll do is, now I'll compute all distances in stage 4. So I'll take one more different font. Okay. So now distance of all the nodes in previous stage. So stage 2. Okay. So if I do this, distance is equal to, let me also take. So how many nodes in stage 2 I have? 3 nodes. Node 1, node 2, and node 3. If I do this, okay, now tell me, from 1, how many outgoing edges I have? 2. So it would be minimum of, it would be minimum of 4 plus, I'm writing it in short, distance of from 1 to 4, right? So I have edge from 1 to 4. So the cost of edge 1, 4 plus distance of node 4 in stage 3. I am at 2, distance of 4, 3. Have I computed this value? Yes, I have computed this value already. So to avoid confusion, I'll write this. Plus, there is one more. How many edges one has? 2. 11 plus distance of 5 in stage 3. So what you'll have, distance of 5 in stage 3. So what is this value? What is this value here? What this value will be? 4 plus, what is 4? 4 plus 18 or 11 plus 13. What is minimum? This is minimum, right? It is 22. I think this goes to 24. So this is minimum. So here the cost will be 22. So what will be 2 and 2? 2 and 2 means here you will have a total. Okay, I think for 2, 4, I forgot the cost. For 2, 4, let us do one thing. For 2, node 2, 4. Okay, let us give some cost to it, a simple cost to it. For this adds 2, 4, let me make a cost 4. So this is 2, 4, 2, 5, 2, 6. The cost is 4. So it would be min of 4 plus the distance. 4 plus distance of 4 in 3. 4 in 3 is 18. 4 plus 18 or 5 plus 13 or 16 plus 2. Okay, this 18, 13, 2. This we already computed. I hope you are getting this. These are the results from the above computations, which I already computed for the next stage. So what this cost will be is equal to what is the minimum? 4 plus 18, 5 plus how much it is? 13 plus 5, 16 plus 2 is 18. 13 plus 5 is 18. 4 plus 8, this is 22. Obviously, I think let us take any minimum possible here. So I think we can reach by 18 here. Okay, so there are two possible. We can take any one of that, but the cost will be 18. The minimum will be 18. So whether you take this path, or whether you take this path, the cost is same. So for 13, what is the 13? I have only one edge in this. So what it is? 2 plus 6. What is this 6? Distance of node 6 in stage 3. This is 2. This I'll make it as red color, so you will understand what exactly I'm doing now. Okay, so what is this equal to? 2, right? So you got this point. Now the only thing remaining, what is remaining now? Let me just get everything here and let me make a space for further calculations. Okay, now it's fine. Okay, so once I'm done with this two, the only stage remaining, I've calculated for stage 2. Now the only thing remaining is stage 1. So for stage 1, okay, distance in stage 1. So in stage 1, how many nodes I have? 0, 1. So I need to find a cost. What I said, it will be minimum of outgoing edges. So what is that outgoing edges? I have 3 edge cost, right? 0, 1. The first is 1 plus, if I select this edge, 1 plus distance of 1 in stage 2. 1 plus distance of node 1 in stage 2, or 2 plus distance of node 2 in stage 2. I need to select minimum of this. 5 plus distance of node 3 in stage 2. So what is minimum of this? I think you can guess the answer by now. Is equal to let me make a space. Okay, is equal to, what is this? Have I calculated this? Yes, I've already calculated this. So it is distance of 1, 2. Did I calculate distance of 1, 2 is 22. 1 plus 22, or 2 plus 18, or I think this min of 2, 2, this will be not 2, this will be 4. We are doing addition, right? So is equal to, let me write it, min of 1 plus distance of 1, 2, 1 plus 22, or 2 plus, either it should be 2 plus distance of 2, 2. What distance of 2, 2? It is 18. This 18, or 5 plus distance of 3, 3. What is distance of 3, 3? It is 4. Okay, what is minimum in this? Minimum will be 9, right? This distance, this will come out to 9. So this is the minimum distance with which I can travel from node 0 in stage 1 to the last node in the last stage, which is 7. Is it? Yes, you can see that this path here is the minimum. You can see here 5 plus 2. This is the minimum path in this multi-stage graph. You can see here, this is the minimum path. Okay, so these nodes, the node 0, node 3, node 6. So this is the path of that minimum. So this is how we get a solution for multi-stage graphs. And why I am calling this dynamic problem, you can see that, look at this approach. Here, I have never computed any value again. I have only calculated distance 4 only once, or distance 4 2 or something. I have only calculated it once, right? Okay. So I hope you understood this. Can you respond? Have you understood this approach? How we arrived at this 9? So for this program, if you ask me to write a Python program, the Python program, what do you think? Will it be too big, too small, or how I can write a Python program for this? Okay, can you respond? Have you understood whatever we have discussed? Shall we move to writing a Python program? I don't think Python program will take much of time. Can you respond, please? Have you understood or not? Okay. So let us quickly see a Python approach. The Python approach to this program, that's not very big. Remember, when you're looking at this, if I ask you to write a Python program, it might look like a very big program, but it is very small. So let us do one thing. Whatever graph I have, whatever the graph which I have here, let us represent this graph as a adjacency list. I mean list of lists, right? So I'll quickly share my PyCharm window, and then I have already typed them as a multi-stage graph, so that I can quickly begin with. Okay, so let me quickly share this. We won't take much of time. Okay, I hope you see our screen. Now, if you look at this, it is exactly the same node, like node 0. From node 0, I have adds to 1, adds to 2, and adds to 3. So what are these 2, 2, 5 they denote? They denote the cost. So how I am representing? I am representing list index as a vertex, list index as a vertex, and at that list index I'll have a list of list wherein it would be of format. So this index will be acting as u, and v I am adding in form of v comma cost. I think I am adding it as let's say v1 comma c1, and I'm doing v2 comma c2. That's how I'm representing the list of list. So index 0 means vertex 0, index 1 means vertex 1. So from index 1, I have adds to node 4 with cost 4. That's how I am representing that. From index 1 means vertex 1. From vertex 1, I have adds to vertex 5 with cost 11. That's how I am replying this. That's how I am taking the multi-stage graph. So I have a last node. What is this last node? 7, right? You see that index 0, 1, 2, 3, 4, 5, 6, 7. Does 7 have, does it have any outgoing edge? No. So the outgoing edge will be null list, nothing. But I want a 7 list of lists. So this represents your graph, and this is roughly equivalent to adjacency list representation of multi-stage graph. That's what I want is. Okay. So now this I have it. Let us do one thing. Let us create a list called as distance. Let us create a list called as distance initialized with by sorry initialized with -1, and how many I'll have, and let's also have n is equal to, let's also have total number of nodes I'll have. The total number of nodes nothing but the multistage graph. So I'll initialize this to -1, right? So I have initialized uh, a list wherein I'll store the values of this computation distance of -1 into n, right? Once I have initialized all to n, what I need to do is I need to start at the end of this node. Let me discuss the approach quickly, then I can write a program quickly. So what I'm doing, I'm storing all this in form of list. Distance, I'm storing it in form of a list. So what I'll do is, this is something I can initialize. Distance of this last node is always 0. I'll initialize it. Then I will start it. For example, it is 0, 1, 2. So what I'll do is I will start at this. I'll initialize this distance of last node is equal to 0. Then what I'll do is I'll start with n minus 2 nodes. I'll start with 6. I will see what are the edges of 6, and based on that edge, I have only one edge plus the distance of 7. See what I'll have 6. So for 6, I am storing the edges, right? Let me also get what I have stored for at index 6. See, at end index 6 in multi-stage graph, where it is. Okay, so this was the code I had, right? The list representation. For time being, I'll just say that. Okay. So if you see the list, okay. So what is it? Index 7, index 0, 1, 2, 3, 4, 5, 6. At index 6, I am capturing this 1. It means that from 6, I have edge to location 7 with cost 2. So what I'll do is I'll start from this 6. I will go to 7, and I'll get this cost here, right? The moment I access this, I get 7, I get cost as well. What I need to do is I need to call distance of 7. Distance of 7 means 0, which I have already stored. Likewise, when I get to 5, what I'll do is from 5, I'll explore all its edges, 7, then distance 7. Then I'll be calculating distance of 5. I'll calculate distance of 4, distance of 3, 2, 1, and 0. That will give me the solution for this, right? So let me go back to PyCharm window, and let me start write the program for that. Okay, so what I do is I'll initialize sync node. Sync node means last node. So what is that? Distance of last node. What is that last node distance of? You can say n minus 1 is equal to what I said, 0. Initially everything contains -1, -1, -1. I have initialized that to the last node to 0. So once I have initialized to last node 0, now I need a for loop. Okay, this for loop I need to run from n minus 2 till I reach to 0. So can someone tell me how can I write a for loop in reverse order? How do I write a for loops in reverse order? Can anyone quickly get me that? For reverse, n minus 2 till -1. Why -1? Because -1 is exclusive. So my loop will end from minus n minus 2 to 0. And every time I write that, I need to decrement this. This will give you the for loop in decreasing order, right? Okay. So now you have done that, I can initialize distance. So the distance of I is equal to. So how do I calculate distance? I need to take minimum, and I need to find sum of the edge cost plus the distance of a node which I reach from this edge cost in the next stage, right? So now let me slightly make complex for you. This would be a good homework for you to understand the syntax. What I'll do is I will something I want to use the elegance of Python, the beauty of Python here. So what I'll do is I'll directly write the list. So min of, I need to choose min of from a list. What this list will contain? This list will contain the sums, right? Let me get that code what I want to refer here. What I'm wanting is I want for example for distance 4, 3 and this, for example, okay, I'll just take one example here. Which I think, okay, I'll take example of distance 2 and 2 because I have. So what I am trying to get here is this, what I wrote in there, right? Just for example. So for example, okay, so for distance 2 and 2, the edge cost plus distance of that, right? The edge cost plus distance of that. The edge cost plus the distance of V in next stage. That's what I need to do, right? So in my case, it would be just distance. So I want to do this here itself. What I'll do is I know from I where I can reach. So from I, what I'll do is I'll put something called a list comprehension and I'll generate all that, right? So if you look here, for each edge at index I, so for each edge at index I need to find the 4 plus distance of 4. It is like 5, it's like 11 plus distance of 5. That's what I have to do. So what I'll do is I'll do a list comprehension. For example, X. If I want to say what is that edge cost, edge is second parameter here. So X of 1 plus distance of this, distance of this. So it would be X of 0 for each X. Explore each X in multi-stage graph of I. That should give you the distance. That's it. So this list comprehension is doing this. It's giving me this values. This 4 plus 18. This is what this value. Likewise, it is repeating for I. So if I start with 7 for 6, so for 6, it takes this, and whatever the value I get, it gets this one here. Okay. So I think this distance should, I think this will give you the cost directly, the distance of all that. Let me print distance and let's see, the first distance should be 9. Okay. So if this is it, let me run this. Multi-stage graph. Okay, so what I have received this distances, right? Now it means that distance of node 0, distance of 1, distance of 2, 3, 4, 5, 6 and 7. Let us see if they are the minimum cost. 9 is what it's, so the moment I get 9, I think we have a solution here. So let us see, let me paste this, go back to the screen here and see if it matches with our observations. Okay, this is what the output I have received. from the program. So do you think it matches? So distance of 7 will be 7. Distance of 6 means, see, I'm talking it in the reverse index, like, okay, distance of 5, 13, yes. Distance of 4, 18. So distance of 1. Distance of 1. I'm not getting distance of this. Okay, this is then, okay. It is distance of 4. Okay, 6, 5, 4. Then distance of 3 is 4, 2 plus 2, yes. Distance of 2, 18. Yeah, so it might have taken randomly from any of this. 18. 1. 122. I think this is 9. This is 11 plus 13. So 11 plus 13 means it's 11 plus 13 or 4. This is minimum. 4 plus 18, 22. And here we'll have 9. It's 5, 4, 4. So this is it. This is a program, direct program for this. And what is more elegant is the Python syntax which lets me write this code. That's it. So this is a graph representation. This is one. This is the only code I think which you get to have here. Okay. Have you understood the program? So if you have understood that approach, this is something you get by, remember, every time it doesn't mean what are the algorithm which I wrote exactly the same steps should repeat. We are repeating that in a program in slightly different way. Now, if you ask me the complexity of this program, you can check. The only complexity is I need to check for this loop. In this loop, I am looking at the vertices, so it will execute v times. So for each v time, here I am doing it for number of edges it has. Okay, so for each edge, for each vertex, I am exploring all of its, I am scanning all of its edges. So almost, so how many times it would execute? So the complexity should be roughly in the order of n square. Roughly in the order of n square. But if I do a further detailed analysis, it could be, I think, so v. For each v times, I am doing e scans. So literally what I am doing is I am exploring this v's and I am also exploring edges as well. So ideally, I think it should be v plus e. It's slightly doubtful about. So ideally, it should be v plus e. This is the most ideal solution, ideal complexity as per textbook definition. But here, I think it should be n square. I think n means almost you can say it is v square. But I still feel the complexity of this program is this. You can later on analyze this, what exactly it is, whether it is v square or v plus e. So I need to analyze what comparison I'm doing. For minimum, if I'm doing list comprehension, if I count this for and for, okay, I think it should roughly come to this. Okay, so have you understood this program? Have you understood the concept? You have understood? Have you understood the program? How many have understood? Just say yes. If you have not understood, just say no. There is no negative marking or anything. If you say, sir, partially, I need to go through recording, then I will understand. I'll go through program, then understand. That's also fine. Okay. So what was difficult in that? Understanding the program or the approach? I think approach should be fine. Approach you all might have understood. Program might have been a little bit complex. Okay, so what I'll do is I'll share this program, the diagram, and also the recording one. Go through it, understand what we have discussed. You can pause, you can analyze, or if you find anything missing or anything wrong explained, you can send me the timestamp in a YouTube video and we can check that later. Is it fine? So, okay, anyone else who understood this, the Python program and the approach? Any student? One, two? Okay. Okay, you feel you will get the complete understanding by looking at the recording and the code again on your own? Okay, so that's fine. So I'll share the recording, the program, and that screenshot. I hope you know the where my programs are stored. It will be on my GitHub repository. Programs I'll share on YouTube. I'll share the playlist where I'm uploading. I hope you have the links to the recordings which I regularly upload. Okay, so that's it for this. I think you can leave. Today there is a little bit less attendance. Why? Number of students attending today are far less. Okay, fine. Yeah. So yes, I'm done from my side. You can leave. No issues.